morning, everyone. So let's start with today's lecture on random matrices and universality. And what I want to do today is to give you a little bit of background on this matrix-valued stochastic differential equation that we introduced already a while ago. And yeah, so maybe I think this is section 3.4. So comments on matrix valued stochastic differential equation. I think I used the shorthand MSDE. And yeah, I just want to recall the beta equal to 1 case. So we had two things here. So the MSDE looked as follows. So we had some diffusion term which came from some Brownian motion, and then we had a drift term which was just minus 1/2. Okay, should be a KL here, and then the diagonal term looked slightly different. In particular, this was kind of the same as we will see in the exercise session today. This will give you in the sense that the GOE is the invariant solution for this. And yeah, we just wanted to have something which is symmetric. What did I? Yeah, so it's KL LKT. So this was say for K smaller than L, K equal to L, K bigger than L, and this was the, so to say, beta equal to 1 case. And then I don't want to go into detail, but similar for beta equal to 2. Yeah, what I want to and yeah, of course these are independent Brownian motions. So and of course this should be a KK, a KT. Okay, and then the importance of this process was what I already stated as lemma or theorem 316, which I just want to recall because we will also use it later in this lecture today. So just sketch it briefly. So beta is in 1 or 2, and HT is a strong solution of this equation that I sketched before, this MSDE. And yeah, and then H0 is in, well, Rn or Cn when beta is 1 or beta is 2. And yeah, well, it should be, well, let's write it like this, complex Hermitian or real symmetric, depending on which case we are in. And then the conclusion is then the eigenvalue process associated with this HT is a weak solution of this DBM equation. That we already looked at for a few times yeah, that we looked on the whole last weeks, right? So these are the two equations, and actually I don't want to really go into the proof here because it would take us well, maybe another 1-2 lectures, and we are running a bit out of time because the end of the semester is coming close. So I just want to recall that we did this in the homework session. We had an exercise problem on this, and yeah, so you might want to take a snapshot here if you want. So yeah, in these homeworks which we discussed 2 weeks ago and last week, we gave a heuristic argument for this, and yeah, so maybe I put it as a remark. So heuristic argument for theorem 316 was given. It was homework 7, exercise 3, and then there was a second part, which was homework 8, exercise 1. So then, in some sense, we gave a very special case, and then yeah, and then maybe I just say that the actual proof is a modification of a proof in the book by Anderson, Giuni, and Saituni. So if you're interested, you can look there. Modification to one of theorem 432. In the book by Anderson, Giuni, and Saituni. And maybe I should say that the basic idea is maybe a bit surprising. So it actually, you go backwards. So in the sense that one starts with a solution. We start from a solution of the equation for the eigenvalues, and then one constructs a weak solution of this matrix valued equation. The equation system up here, and the beta equal to 2k similarly, and then by the uniqueness of these equations, you get that you also get that you also had a strong solution before there. So that's so in some sense one constructs it backwards, but that's of course by the uniqueness the same thing. So yeah, and then it constructs a weak solution to the matrix system. Okay, and before we continue, I want to state something as a lemma, which we will actually prove today in the home exercise session. But this we will use many times well, a few times today. So this will really be an important thing, and it gives us, in some sense, a solution. It will give us a solution for this, but just in a sense of distribution, in a distributional sense, meaning that one can specifically define the distribution, or there's a specific formula which gives us the distribution of the solution, ht there, and but actually in the exercise we will kind of integrate the equation and then determine the solution, because it will, in some sense, one has to compute an integral there, an integral with respect to Brownian motion, and that one can only do in distribution. So For that, we assume that we have it can be a random matrix, the initial condition, but it should be Hermitian. And independent of the Brownian motions. Yeah, maybe I should write this a bit differently to distinguish the two cases. And independent of, so there are two cases. So when beta is 1, then I have only one set of Brownian motions. And then, or beta is 2. From this matrix stochastic equation, stochastic differential equation, and HT should be a solution of this MSDE with the initial condition H0. And then we have the following results. So the first part will give us the result that I just explained in words. So if HT is the solution, then in distribution it is the same as e to the minus t over 2 H0 plus 1 minus e to the minus t to the 1/2 times u, where u is either GOE or GUE. Namely, if beta is 1, or it's a GUE matrix if beta is 2, and of course it's independent of H0. This I should is equal to GUE, and U is independent of H0. Okay, and that holds for all t. Okay, yeah, maybe you want to take a picture here. And then the second part will be that we'll say that if I start from a Wigner matrix and then I evolve it along this flow, then I keep a Wigner matrix. Then the HT stays a Wigner matrix for all times. So that's of course immediate from the part before. So if H0 is a Wigner matrix, then HT is also a Wigner matrix. For any positive t. And yes, I already said the proof. We will also homework problem, and we will discuss it today in the exercise session. Okay, and yeah, so that's all I wanted to say about this matrix flow, and it will come in today later. Hopefully, we will be sufficiently fast. And then what I want to do next, I finally want to come to an application of this whole Dyson-Brownian motion business, and that what goes under the name of edge universality, and that's the next section. So I think this is section 4, and that will give us the fluctuation the largest eigenvalue a Wigner matrix. And yeah, maybe the other buzzword there is this edge universality. Yeah, universality here has the same meaning as we had it before in the bulk. So it means that you can actually explicitly compute something for the in the Gaussian case, and then one can prove in a second step that actually you always get the same result as the Gaussian case, at least in, we will discuss it here for Wigner matrices. So recall that by eigenvalue rigidity, I have the following. Now I change a little bit the notation to be more consistent with what we had before when the lambda ones in this set sigma n were ordered. So now the lambda n is the largest eigenvalue. And this is stochastically dominated by n to the minus 2/3. When lambda n is the largest eigenvalue. Something is not readable, please complain. Of a Wigner matrix. And yeah, for that we somehow need that the 2 minus gamma n, these were the deterministic locations. That this behaves like 1 over n. So this error between, you remember that we always had the, maybe I should put it here on the side. What we always said is that that this here is small, so lambda I was the random object, so lambda I is the eigenvalue, and gamma I was the deterministic location. And now here I put a 2, but yeah, well, if you look at the definition of the gamma I, then you easily see that the 2 and gamma n are sufficiently close so that this here is still valid and directly follows from our definition of the from our statement in eigenvalue rigidity. And now we already saw in the bulk that there you had somehow at least the eigenvalue spacing was on the same order as the spacing between the gammas. And here you will see something similar, namely that this here is sharp in the sense that when you multiply, so you take the largest eigenvalue of a Wigner matrix, and then you subtract 2, and you multiply by n to the 2/3 plus 2/3. Then from this here you would expect that this is of at least in stochastic domination sense of order 1, and actually it is of order 1 even in the stronger sense, namely in the sense that this even has a limit, at least in the Gaussian case. So in fact, and that's what I want to state now, in the Gaussian case, so U1 should be GOE and U2 is a GUE. So we have that, as I said before, I want to look at this object, lambda now of this U beta minus 2 multiplied by n to the 2/3. If this is a good object, then one would hope that this here has a limit in the sense like that this distribution, the distribution of this here has a proper limit, and that's actually the case. So if I take the probability that this is smaller than S, say, and then of course I have, as always in random matrix theory, or at least in what we are discussing here, n goes to infinity, then we get that this has a nice distribution function, which is the so-called Tracy-Widom beta law. So acting a Gaussian case for all S in R, and yeah, beta is 1 or 2. And I owe you an explanation what this here is. So this is the distribution function of the beta, well, maybe it's more better to Tracy William beta distribution. Okay, so these are honest. The definition is a bit complicated, so they're defined by solutions from some stochastic, some ordinary differential equations, which don't have an explicit solution, but they appear many times in many instances, and actually they appeared first in this random matrix business precisely in this kind of statement that was proved by Tracy and Widom for both beta equal to 1 and beta equal to 2 in the 90s. And there, that was the first instance where these Tracy Widom distributions appeared. But since then, they have been found in many, many situations where you have you look at certain observables of strongly correlated random variables, as in this case, the eigenvalues. So here you look at somehow the maximum of the eigenvalues. In these kind of situations, this Tracy Widom distribution appears. And also in particular, it's important in random matrix theory because it has this universal feature, as we will see next. And yes, I think that's what I wanted to say here. And yeah, maybe I can give you a very rough sketch of them. Well, they have a continuous density, even bounded. So maybe I can try to sketch them. Let's see how this will look. So actually, I should put this, do it a bit differently, namely put 0 here in the middle, here 0, and then the beta equal to 1 looks maybe like this. So this is the F1 prime, and then beta equal to 2 as a switch sharper, and a bit more negative. So that's F2 prime. Okay, this is a rough sketch. You can find some pictures on the web or in various books that we have in the references. And yeah, this I want to call star, and actually this here I also want to give a name. So yeah, I want to call this eigenvalue rigidity, or maybe better H eigenvalue rigidity. And then yeah, there are two remarks which I want to make about stars. So of course you have a similar result if you look at the smallest eigenvalue. A version of star, and then lambda 1 u beta minus 2 plus 2. So the the smallest eigenvalue converges to minus 2. So I have to shift to with plus 2 holds. And yeah, this here is then the smallest eigenvalue. And one can write it similarly. I mean, you remember in the bulk, you remember that in the bulk we used K-point correlation functions, and here you can do the same thing. It's just that this here is maybe somewhat a bit nicer to state. So result similar to star exists for local K-point correlation function at 2. So the idea there is similar, or well, maybe you want to take another snapshot here. So the idea to prove this is in some sense similar as what we've seen in the bulk to compute to see the sign kernel. So here you can do some similar computation, but then the limit is in some sense more implicit because it's only the solution of these Perle-Levy equations. And but what we will be interested in is whether this is universal in the sense that can I replace the U beta here by any Wigner matrix, and do I then get the same result? And that's what I want to do in the next, I want to state in the next result, which will be, well, maybe one of the most important results in the whole course. So instead of star, we well, instead of proving star, we show that the limit is universal. So that will be the next theorem. So that's theorem 4.1. And that goes under the name of edge universality. And so we now take an arbitrary Wigner matrix. And then we make two sets of assumptions. So somehow we need to be once in the real case and once in the complex case. That's kind of similar as in the bulk, where we had to distinguish there were these 4-moment matchings, and either you had 4 moments matching with the GOE or with the GUE to get the Gaussian limit. And so yeah, the first case is somewhat similar, simple. So we have H is just a real matrix, and that's kind of, yeah, that's the analog of the beta equal to 1. And then we have a second set of conditions, namely, so of course they are mutually exclusive. So H is can be a complex matrix. Then we want that the real and imaginary part are independent. So the whole family of real parts and imaginary parts are independent. And then we need a further condition, namely to make sure that it's in fact not a real matrix or not a purely imaginary matrix. We need another condition, which I want to write in that form maybe, so that the expectation of Hij squared is 0. So of course, if Hij would be real, that would imply that Hij vanishes. But now Hij is complex, so that's the square of a complex number. Then you have real and imaginary part, and in fact, this is maybe I should say this condition here is in some sense equivalent to the fact that the second moment of the real part of Hij, well, now that's a real number, I can square it, but it's the same as the second moment of the imaginary part. Okay, so these are now honest real numbers. So just as a remark what this means. And in this case, we have the following statement. So then we find epsilon bigger than 0 and the delta bigger than 0 such that the following holds. So so what I'm interested in, let me write it here in the middle, is the probability that when I multiply lambda n of H minus 2 by n to the 2/3, and look at the probability that this is smaller than S, then I want to compare it with the same expression where the H is replaced by a U beta. And I will do that in 2 steps. Namely, I will have an upper and a lower bound, which will look as follows. So I have the same expression, but with U beta. This is smaller than S minus, and now I get the first error term, n to the minus delta minus n to the minus gamma, n to the minus epsilon. And then I have the same, well, I can maybe just copy it. Now I have to change something, namely here I have to put a plus and here I have to put a plus. Okay, so that's the kind of statement that we're interested in here now, and this should hold uniformly for all S in R. Okay, so yeah, maybe you want to take a snapshot now, and then I'll explain it again a little bit. So this is the quantity that we're interested in, right? So that describes the probability distribution of the largest eigenvalue of H. And we're interested in the large N regime, and then we compare it here with the lambda N of U beta, so here and here. And as a lower bound, we get the same thing, but then we have to shift the S by n to the minus delta to the left, and we also have to make the probability by n to the minus epsilon smaller. And then as an upper bound, we get the same expression, but both times here with the plus. And then the first remark is that, of course, this is enough together with star, we get that we can actually get that it's the same, that also this here converges to the Tracy-Widom distribution, because the F beta is continuous. So I guess this you can all convince yourselves easily. So maybe the first remark I want to make. So theorem 4.1 star into continuity of F beta imply that they have the same as in star, but now for the Wigner matrix H. Lambda n H minus 2 as F beta S when n goes to infinity for all S in R. Okay, so that's the first remark. Then if you compare it with the corresponding result in the bulk, so in the bulk we, for example, looked at the k-point correlation functions, then the surprising thing here is that you don't need any moment matching up to order 4. And in some sense that has 2 reasons, namely because our proof will be in some sense a bit different from the proof in the bulk. So we will also use these kind of moment matching ideas, but that will only be one part of the proof. But in fact, you can also, if you work hard enough and you go through these moment matching proofs, then you can actually directly get rid of this moment matching condition. So I want to say that in the following, and that comes because the off-diagonal entries are smaller because we're now close to the edge of the resolvent. So of course the resolvent will be the main tool that we will use in the back. So 4.1 can be proved without matching moments up to order 4. Similarly, theorem 2.2. That was the bulk universality in the form with the matching form, which matching moments up to order 4. And the reason is that, yeah, as I said, the off-diagonal entries of the resolvent are smaller, so certain estimates will be better, and then you don't need this kind of moment matching. Since off-diagonal entries of resolvent are smaller close to the edge, so that by edge I mean with plus or minus 2. But we will actually follow a different path because we will use a different tool. Well, that's why we spent the whole last weeks on this Dyson-Brownian motion. Yeah, but our proof of theorem 4.1 uses these Dyson-Brownian motion ideas. And yeah, in particular, this results from sections 3. We need one more tool, which I state next. And the main reason why we're doing this is because this kind of approach gives you a much more general angle of attack for various other problems. And so this is now this is somehow commonly used in random matrix theory to prove many kinds of universality questions in different aspects. So yeah, this I want to say now. So this approach can be used in many other situations as well. Maybe to give you some examples. So one can of course do the bulk without matching moment up to order 4. So in the bulk you cannot improve this moment matching condition. So there really this 4 is if you just use this screen function comparison approach that we used in the beginning of the lecture, you cannot do better than this 4 moment matching because there you don't have this improvement here that the off-diagonal terms are smaller. So but we don't do this argument in the bulk here because that's some sense more technical than what we will have to do later. And also it can handle many different situations. For example, one could think about relaxing our assumptions, relaxing the assumptions of a Wigner matrix. You can of course ask the same question. You can ask what is the distribution of the largest eigenvalue, or what is the bulk distribution, and in general you get the same answers. And this can also be handled by this approach that we want to study now. So for example, you could impose such a condition that you take 2 indices I and j and other indices k and l, and then you start looking at the situation where the variances are different, and then a priori you would expect different behaviors, but actually these universality questions are so rigid that even if you relax these kind of assumptions on a Wigner matrix, then this is still correct. And now for the rest of essentially for the rest of the lecture, for the rest of the course, I want to restrict to the case when beta is 1. For the proof, we restrict to beta equal to 1, so that corresponds to the theorem 4.1, the first case. But it's actually not a severe restriction. It's mostly to make the notation easier. You've seen that whenever we have the beta equal to 2, then one has to look at real and imaginary part and treat them somewhat carefully. And this I don't want to do here. And actually, historically, beta equal to 1 has also been the harder case. So in the case beta equal to 2, there are certain other approaches which were first found or developed, which could be used to prove universality in these kind of situations. So in some sense, so from the random matrix perspective, beta equal to 1 is also the more, yeah, in some sense, the harder problem. And maybe before the break, I want to still state one result or one important tool that we will need. Yeah, sorry, maybe you want to take a snapshot here if you haven't done so yet. And that will now be the main result of the, well, about Dyson-Brownian motion that we will prove and prove in the next, well, last two lectures. And it will be the strongest result that we will see about Dyson-Brownian motion. It will basically tell you that if you start from two initial conditions, then after, with a certain speed, the solutions will converge to each other. And that will give us a way to analyze universality. So important tool for the proof of theorem 4.1 is the following. So it's theorem 4.2, and that goes under the name of relaxation, because that indicates that something relaxes to some equilibrium. And it's the relaxation of this dBm dynamics. So what does that mean? So we start from two sets of initial conditions. So now the lambdas are always increasing, and the same thing, I have initial conditions mu. Yeah, we restrict to, should have remarked here that beta equal to 1 and beta equal to 2 works completely analogously. So all results I state now have a clear version for beta equal to 2, and that the proof is actually exactly the same. So yes, so we start from two families which are eigenvalues of two Wigner matrices. Be the eigenvalues of a Wigner matrix, maybe W. And well, maybe it's better if I call this H0 and a GOE. And then we evolve both of these sets of eigenvalues with the dBm. So let lambda t, lambda mt, and mu t mu nt. Yeah, maybe I don't want to write them out again. Be the solutions of dBm with initial conditions lambda 1 0, yeah, one would expect, and mu 1 0, mu n 0 respectively. Okay, so we start from two sets of eigenvalues and then we evolve them with the DBM, but now we take the same Brownian motions as we've already done a few times. So should maybe say that same Brownian motions for evolution of lambda t and mu t. Okay, and that gives a very nice coupling between these two solutions, and that will allow us to get the following result, namely that they converge somewhat fast to each other. So then, for each d bigger than 0 and epsilon bigger than 0, we have the following, namely that the probability that I take lambda k minus t minus mu k minus t is smaller than n to the epsilon divided by n t for all k from 1 up to n, and all t between 0 and 1. This probability is 1 minus order n to the minus d. So that's in some sense some stochastic domination of the some boundedness of the supremum of the difference of the lambda case minus the mu case for all t between 0 and 1 and for all k. Okay, so that really gives you this kind of result that I meant, so that if you start the same DBM with the same Brownian motions from two sets of initial conditions, then they will converge to each other, and here you will see that they kind of converge quite fast. So they converge actually with a rate which is something like 1 over n times t. Yeah, that's actually quite fast. And later we want to use this in such a way that this difference becomes smaller than the fluctuation of the eigenvalue we expect at the edge. So that means if this, according to the results that we had before, in particular to the Gaussian result, one would expect that these individually the largest eigenvalue fluctuates on a scale n to the minus 2/3. So that means we have to make this here smaller than n to the minus 2/3. So the t will only have to be n to the minus 1/3 or a bit bigger, and that will already give us convergence. And then you see that because the U1 is a GOE, actually even at time t you still have the eigenvalues of a different GOE then, and that will give us the way to compare these two results. And yeah, that's where we'll continue after the break. So let's maybe continue at 10:20, and then yeah, the proof is we will do in the next section, and we first want to prove the universality at the edge, and then postpone the proof to the next lectures. Okay, so if there are no questions or comments, then I would suggest to meet at 10:20. Okay, I hope everyone is back. Then let's continue. Yeah, so before the break, we discussed this theorem about the relaxation of the Dyson-Brownian motion dynamics, and I made a few remarks, and I just want to list them here for completeness. So as I already said, we will prove this result in the next section. So I guess starting from next week. And yeah, then the other thing I said is that if, since initially you started from a GOE And then if you use the flow that we used, you can see that by the uniqueness statements, that the mu t are also eigenvalues of a GOE matrix. So I want to formulate it as follows. You need two inputs there. So this is lemma 322, the first part, and theorem 316, the one I recalled in the very beginning. And I didn't in the very beginning today, which I did not prove. So from this we know that mu t has to have the same distribution. So even as a vector, as a joint distribution sense, as the eigenvalues of a GOE matrix. So that just comes from the fact that we can, along the matrix flow, we can control the distribution, and we can, from this formula, you can directly see that if you start from a GOE matrix, then the evolution will be invariant in the sense that along the flow you always get a GOE matrix, and then you can use theorem 316 to get from the matrix flow to go back to the eigenvalue flow, and then by uniqueness you get that they have to be the same in distribution. And the other thing was about the this the speed of convergence here, and how large one wants to choose t. So since mu t fluctuates on a scale n to the minus 2/3, this is by this equation star about the Tracy-Widom distribution. Theorem 4.2 is useful at the edge. So so to say something about the lambda n of t, if this n epsilon n times t is a bit smaller than n to the minus 2/3, and then I want maybe just send by an epsilon in the exponent, so that's equivalent to t being bigger than n to the minus 1/3 plus 2 epsilon, right? So just a bit bigger than n to the minus 1/3. So that's actually after a rather short time. Okay, and so yeah, now you might want to take a snapshot, and now we want to use these kind of tools to prove theorem 4.1. And along the way, we will have to introduce a few other tools which we'll prove later, or which which are somewhat similar to things that we've already seen. So then there I want to omit the proof. Okay, so let's start with the proof of theorem 4.1. And as I said before, we will only consider the case when the beta is equal to 1, and the rest has a very similar, on the other case, so beta equal to 2 works very similarly. And then first, I want to assume that the S is large, so we will distinguish two cases for the S. So the simple case is when the S is very large, namely when S is bigger than n to the alpha, for some alpha bigger than 0. Then this implies that just comes from the eigenvalue rigidity, as we will see, that both of these quantities that we want to compare with, so lambda n h minus 2 smaller than s, is the same as lambda n, the GOE, minus s, even if I add this n to the minus delta here. And this actually holds for all, this is of order n to the minus d for all d positive, and that that just comes from the eigenvalue rigidity of the largest eigenvalue, which holds, of course, for the GOE and for the Wigner matrix. So this is what I stated in the morning, in the beginning. So that was this edge eigenvalue rigidity. So this case was simple. The other one needs more work. So we now fix some positive alpha, and we assume that the S is smaller than, assume that in absolute value, S is smaller than n to the alpha. So yeah, maybe of course here I should have said, so this holds for both signs of S. So if the S is negative, this of course directly follows, because this here is order n to the minus d, and this here is also order n to the minus d. And when the S is very large, then both of them are 1 minus order n to the minus d, both of these things. So then you have a 1 on both sides plus an error term of this order. So this is correct in both cases. Okay, and now in the case when S is smaller than n to the alpha, we will introduce now two test functions, or maybe few test functions, which help us to kind of rewrite this probability here in terms of expectation of these test functions. And then for expectations of test functions of eigenvalues, we can then we will first use some moment matching, theorem. And then later we will be able to use the matrix flow to achieve actually this kind of moment matching up to a sufficiently high order. Okay, so in order to do that, we first fix a scale eta, which I will choose later. So it will be between n to the minus 1, which is the spacing in the bulk, and the n to the minus 2/3, which is the spacing at the edge. And we take functions fi, which are defined as follows. So it's some kind of natural, in some sense, smoothed out indicator function. So when the x is big, namely it's 2 plus s to the minus s times n to the minus 2/3, and it's 0 otherwise, and in between you just interpolate increasingly. And here it's if this is smaller than eta. So if the eta scale just separates them, and fi non-decreasing otherwise, and the f2 is a shifted version. Of f1, so it's shifted to the right by the scale eta. Okay, so these f1 and f2 will give us the upper and the lower bounds on the probabilities, that as we will see soon. Yeah, we need some technical conditions on the derivatives, but they're easy to achieve. So we just need that it's a bounded function, that and that its derivative is at most 1 over eta, and the second derivative as most 1 over eta squared. And so that's one set of test functions, and then we need another set. I will give you the formula in a minute, and then you will see why these functions are helpful. And then we have another smooth, yeah, of course, this. And yeah, maybe I should have marked it here. So the fi's, they should also be smooth. And fi, put it here. smooth functions defined in this way. And then now they were non-decreasing, capital F is non-increasing. And it should have the following properties. Yeah, and the derivatives need to be bounded. So it's just a nice, sufficiently regular, smoothed out test function. So I again define it only for large and small values, and then in between one can interpolate. So if x is smaller than 0, then it's 1, and if x is bigger than 1, then it's 0. And then I have the following formula. Now I have these two f's, and the important formula will be the following. So as I said before, I want to have a different expression for this quantity. That's the one we're interested in, right? And as a lower bound, I claim that this is smaller, this is bigger than the expectation of capital F applied to the following quantity. I take F1 lambda I H, sum up all the F1s, and then I apply capital F. That's the upper bound. Sorry, that's the lower bound on the probability. And the upper bound looks the same, except that then we have an F in F2. So F2 lambda I of H. Okay, and yeah, this will be very important relation. Maybe I make it in color, then it's easier to find it again. And maybe as a comment why this is correct. So if I just take this part here, then this is of course 0 if the lambda n of H is bigger than 2 times s to the minus 2/3. That just comes in from the definitions of the F1 and the big F, and it's smaller equal 1 otherwise. So then I take the expectation, and then of course I get this first inequality here. And similarly, you get up here, you get that this is 1 if the lambda nh is actually smaller than the. I need more space. 2 plus s into the minus 2/3, and otherwise it's positive. So that proves this hash, and so that gives us a way to express the probability in terms of expectation of smooth test functions. And as we've seen already before, is that these expectations of test functions, of smooth functions, one can control much better, because one can there use something like Hepper-Sjöstrand to express it in terms of the resolvent, and then the resolvent we can control by local law and similar tools. And that's actually what happens in the next proposition. So that will allow us to compare this probability here for different for 2 different matrices. Therefore, we can compare this probability. So the P lambda nh s smaller times n to the minus 2/3 for 2 different matrices H. via the next proposition. So that looks as follows. So it's proposition 4.3. So there is a positive C such that we have the following. So such that if we have another Wigner matrix, real symmetric, is another real symmetric Wigner matrix, which has the following conditions. So if it's also real symmetric Wigner matrix, then it matches the matrix H at least the first and second moment. Then we also want that it matches the third moment of H. And we want that the fourth moments are at least close. Minus, this is smaller than, say, T divided by n squared. So recall that by the scaling of a Wigner matrix, these fourth moments are of order 1 over n squared. So, or by the assumption that we have bounded moments, and then the scaling of the entries, we get that these guys here are both of order 1 over n squared. And here we want that with some small t, or well, with some t, they're actually close. Okay, and then yeah, of course we want this for all entries I and j, and some t bigger than 0. And then in this situation we can control the difference between the expectations of these test functions that we looked up yet before. So I can actually write it as trace fk of h. That's how they looked. And that's the structure of them. Expectation f of trace fk w. This is smaller than, there's some n to the c, but c will be something small. T over n eta plus 1 over n eta squared plus 1 over n, and this holds for k1 and 2, these functions we had before. Okay, so I'll again omit the proof here because we don't have time to do all of this, and I want to focus on these Dyson-Brownian motion ideas. But one can actually, I guess one can give at least a short idea, which is maybe convincing for at least some of you. So you'll probably remember this Heffler-Sjöstrand formula from the last term. So that this one we used to formula. So this one we used in the proof when we went from the local semicircle law, when we transformed this information about the local semicircle law to information about the eigenvalue counting function. So how many eigenvalues lie in a small interval. So that was called the semicircle law on the small scales. Then we used this formula to transform information from the resolvent to information about the number of eigenvalues in an interval. And we actually also proved it on a homework. So it was actually exercise 23 on homework 7 in the last semester, last term. So so that gives you, as I said, a way to transform functions into integrals over the resolvent, and then you can use your information on the resolvent. And to study the resolvent, one can then use some green function comparison, which was similar to the proof of we also use these kind of ideas together with the moment matching in similar as for theorem 2.2 in the beginning of the semester. Okay, and yeah, if you're curious, this very precisely as it's stated here, this is proposition 5.1 in a paper by Paul Bourgaert. It's called extreme gaps between eigenvalues of Wigner matrices. There he considers a bit more general setup, and yeah, you can find the link on Moodle, or if you search on it on the web, you will also find it. And there he considers a somewhat more general setup, but in particular it contains what we proved there before. And yeah, the idea is similar as to what I said here. So you do some green function comparison, use the moment matching conditions, and of course the local semicircle law. And okay, so now so now I take this for granted, and then I'll omit the proof here. So now we have we have some information already how we can understand this quantity here. So we have this result about the Dyson-Brownian motion, which gives us that if I run the Dyson-Brownian motion for for GUE initial condition and for some Wigner matrix initial condition, then if I run it for time, or a little bit of time, then I will get then I will see that the lambdas, they are close to the mu's, which are the eigenvalues of the GOE matrix. And then on the other hand, I know now by this proposition 4.3, that if I have two matrices which match moments in this sense, so the first three moments are matched precisely, and then the second moment is close, then I can somewhat, together with the formula here, I can compare the probability to have to understand the largest eigenvalue. I can compare them very well here. Actually, when we will choose the t and the eta in such a way that this here will be small. So that gives us another important input. And if one puts them together, then we're actually looking for the following object.
Sorry, I have a question about the proposition. Shouldn't C there be something small?
Oh yeah, of course. That should have a minus. Sorry, yeah. I mean, C is no, sorry, yeah. C is meant to be small here, so that's maybe not. So you should think of it as being some epsilon. I don't know, some 1/10 or 1/100 or something like this.
So, like, is there any bound in this proposition for the C? Because as it was written here, it can be a.
Yeah, it can be anything. Yeah, so there. Yeah, well, I don't know. I guess I can put something like. I think you can even choose it. Well, let me formulate like this. I think it's clearly correct if the C is between 1/100. So, and I think that will clearly do the job. Okay. Yeah, you're right. I mean, one has to make clear that this is actually a small thing, and that's not. It will not blow up. But yeah. Okay. So so yeah, what was I saying? So so we are now somewhat looking for an auxiliary Wigner matrix which has the following properties. So we need a Wigner matrix W such that the following holds. Well, first of all, we need that its eigenvalues have the same distribution as lambda t from theorem 4.2, at least for some t, I don't know, let me write it like this, or let me maybe like this with the, I don't know, 2 epsilon. That's what we had before. That's one condition, because then we know that that the lambda t eigenvalues, they are very close to the Gaussian to the eigenvalues of a GOE. So these ones we will understand. And the second one is that it satisfies the conditions of this proposition 4.3, because then we can compare it with the matrix H. So, and it satisfies the conditions of proposition 4.3. And this is actually, this we will do via the next lemma. So that's some interesting observation. Namely, it means that if you start the matrix flow from a cleverly chosen Wigner matrix, then you can actually approximate your first. Well, you can match the first 3 moments precisely, and the 4th moment you can match up to this order t over n squared that we were looking for before. So for each, well, maybe I should formulate it more precisely. So there is a t0 bigger than, there's a constant, well, it's a constant. There's a constant t0 bigger than 0, such that for each t in 0 t0, there is a real symmetric Wigner matrix W0 in this which satisfies the following. Well, such that now I consider the WT, which is defined as what we expect for the distribution along the matrix flow. So and then I call these entries Wij of t. And these entries satisfy these moment matching assumptions that we had before. So they satisfy that the expectation of Wij t to the k is Wij to the k for all k from 1, 2, and 3. And for the 4th moment, we don't get that they match, but we at least get that they are close. Namely, this is Hij to the 4 plus something of order t n squared. And that's for all I and j. And yeah, and then as before, the U is a GOE matrix. So here U is it GOE matrix? Okay, and yeah, what you recognize is that this is the, well, the right-hand side has the same distribution as what we would expect from H. So the right-hand side here has the same distribution as what we expect from the matrix flow if we start the matrix flow at W0. So the WT will have the same distribution as the matrix flow. And then we know that the eigenvalues of this matrix flow have the same distribution as what one gets out from the Dyson-Brownian motion. So from that point, that gives us then that we can apply part A here. And then obviously also part B is satisfied. So that will give us this matrix that we want. And this lemma we will actually do as a homework for next week. It's actually some nice construction on some basic random variables. So that will be on the next homework. And now we can conclude the proof by choosing the t and eta properly. So let's go through this. So we now choose the t to be n to the minus 1 over n to the minus 1 over 9, and eta to be n to the minus 8 over 9. So remember that the t had to be bigger than n to the minus 1 over 3 to apply this relaxation of the Dyson-Brownian motion, and the eta had to be smaller than n to the minus 2/3 to identify the correct scale. And now we use this equation sharp, which I had before, which compared the probability with the expectation, and these two propositions just before, so proposition 4.3, and now this last lemma, 4.4. We choose, sorry, there's something missing, namely an obtain. And obtain from sharp and these two results that the following holds true, namely that if I test this against f1 lambda I of wt minus, and then I have an error term. If you compute it, it's minus 2 over 9 plus c. This is smaller than the probability we're interested in, so lambda n of h 2s times n to the minus 2/3, and it's smaller than, and then, well, the same expression here again, but now with the positive error term. So equation f, and we have the f2 function lambda I wt sum over I plus this. Okay, so now we are already one step further, because now we can compare this probability lambda nt lambda, the probability for the eigenvalue of h, we can compare it with something that only depends on the wt. Okay, so the wt is already the good object that we understand, and so from this we are already half the way through. But now, of course, this we would like to express again with the probability of lambda n of wt now, because that's the good object we understand, and this we can actually do by using this sharp again, but now with a slightly different function, because we have to shift it a bit. So So we use sharp again with h replaced by wt, and the function shifted by and f1, f2 shifted by plus minus eta. If we use this this sharp here, then we can express this here back. Then we get a lower bound on this here in terms of a probability of lambda n of wt, and we get an upper bound on this here also in terms of this probability. But then the probabilities are slightly shifted, so it looks, or the places where you evaluate the probability are slightly shifted, so it looks as follows. So I have the probability of lambda n wt is smaller than 2 plus s n to the minus 2/3, and then now minus eta. Because of this shifting, I have to move it over. The error term here stays the same. This is smaller than the probability that already had before, the one we're interested in. And it's smaller than the probability of lambda n wt smaller than 2s, and now we have to shift it other direction. So there's a plus eta here, and then plus the other error term. So that's already good. And now we do what I said before, namely we compare. Now we know that this lambda n of wt has the same distribution as the lambda n of t if I started at the w0, and then we can compare this with the mu's, which have the distribution of the eigen of a GOE matrix. So now we are almost done with the proof here. So now I combine a few important results that we stated before. So theorem 316, 315, and then this lemma 322. We get the following. We get that in distribution, lambda n of t is the same as lambda 1 of wt up to lambda n of wt. If the lambda t satisfies the dBm equation with a special initial condition, namely with the initial condition that everything started from the eigenvalues of w0. Okay. And as I already said before, the mu t is in distribution the same as the eigenvalues of some GOE matrix. And then we can use this relaxation theorem that I mentioned before to conclude actually the whole proof of the at universality. Hence, by this theorem 4.2, we have the following. So, so by 4.2, I know that inside this probability, I can replace this here by the lambda n mu1. Of course, I have to add here another error term, and the same here. So that's what this theorem 4.2 tells me. And the error terms look as follows. So n to the 2/3 lambda n u1 minus 2 smaller than s minus n to the so there's an error term which comes from the eta here, and then there's an error term which comes from this theorem 4.2, and both combined have this shape here. And I have a plus C. And then, yeah, maybe write it in a new line, then it's a bit more transparent. So this is smaller than n to the 2/3 lambda n h minus 2, smaller than s. So I just wrote it wrote it in the way we were used to it, and then I can rewrite everything in the same way. And then I get here the lambda n of u1 again, minus 2, and then it's s plus 10 to the minus 2 over 9 plus c, and then outside I have the same error term as well. And that's what we wanted. And yeah, as Celia mentioned before, the important thing is that, of course, the C here has to be smaller than this 2 over 9, but that's correct. And actually, I think the previous theorem is even correct with all positive epsilon, so you can choose it as small as you want. Okay, so that's the proof of this theorem 4.1 of the edge universality. And then next week, or the last 2 lectures, will be devoted to the proof of this theorem 4.2, which turns out to be one of the main ingredients here. I hope the other ingredients, we will either discuss them on the homework, or they are at least somewhat clear from previous results, from previous things that we've proved, so that you're convinced that they are correct. And yeah, so if there are no questions or comments, then I would suggest to meet at 20 past 11 for the exercise session, and there you can of course ask me also more questions there.